notes right here. You'll see that I have some new gifts for you. Pretty sure I passed this out. Let's see what happens. Yep, there we go, Adam has them. Okay, and it is under energy and work. All right, so it's kind of important, I think, to note that as we look through this whole year, it's like one long story because everything sort of fits together if it goes right, right? And that's how you start to know when you really understand this is when it starts to all fit together. Because we started off talking about, okay, well, how are we going to describe things that are moving? What is motion? And then we look at speed and acceleration and things like that, how fast things change their speed with acceleration. And then we looked at, okay, well, why do things move? And that for us, the movement forces, and if you want to just pick the test on. Okay, and now we're kind of in the realm of, okay, well, yeah, okay, they're moving, so now what? Right? Why do they keep moving? How do we get things to continue to move, and why do they move sometimes and not others? And that brings us to energy and work and momentum and these things. All right? So, here we go. The first issue that we are going to look at is something called momentum. And momentum is going to be with a small p. Now, you all probably use this term quite a bit, or at least have heard this quite a bit, right? In sports, doing stuff there. This team has the momentum, right? What does that mean?
Like they have energy and like forward. Like they have something that's like pushing them up.
They're moving forward, right? This the mass with yes. Let's see the pass. Okay, so this is the idea with momentum is that it's something that's moving, right? And if something has more momentum, it means it's moving more. In other words, it's kind of harder to stop, right? And we know that from our talk of Newton's laws, and that's true, right? So momentum then is just this mass with a speed, mass in motion. And the more that something gets moving, the more momentum that object has, right? And so we're going to multiply this mass times the velocity. And use this little symbol P for momentum, right? Now, the units then for momentum are right here with kilograms times meters per second, right? And that's just how we describe momentum. Now, the momentum is an interesting point in that it's going to describe this motion nicely. However, really what we're doing is we're building this up to our talk of energy because that's really where this is going. But it's important to note that with the formula, right? The formula is mass times velocity. So that tells you that when you have, let me see if I can find one that works. Okay, then neither one of those affects the momentum more than the other. Okay, so you can change momentum two ways, and that changes it equally. You can change the mass of the object, or you can change the velocity. Right? Now, what happens though to the momentum when things kind of run into each other? Well, the momentum then is going to be transferred from one object to the other. So if this one is stationary and we have this one run into it, what happened to the speed of the first car? It slows down, right?
Yep.
So what happened to the speed of the second car?
It speeds up.
It started.
It starts up, right? In the beginning, it had zero. The second car had zero velocity. So what was the momentum? Zero. Okay. So if something has zero velocity, it has zero momentum. All right. We would say if velocity equals 0, then object has no momentum. Momentum. Okay, so I'm sorry. Yeah. So if the velocity is equal to 0, then the object has no momentum. So when we have our collision there, now what happened was with car A, the first car, the car that was rolling, slowed after the collision. Car B started moving after the collision. And Newton's laws told us that, well, that thing was at rest until something acted on it, and that car was the one thing that acted on it. Okay, fair enough, but let's get a little bit more specific. So what happens here? Well, if this car has momentum, a certain amount of momentum here, when it hits this car, it's going to transfer some of the momentum to it. It's not going to lose momentum in the whole system, but some of the momentum is going to go to this car. But now we have partial momentum for both of the two cars. So we also know that the mass does not decrease. So what has to decrease? If you look at the formula for momentum, if the mass does not decrease, then what has to decrease? The velocity. That's why that first car decreased its velocity, because some of the momentum was transferred to the second. All right? Now, because that car suddenly had momentum, that meant that it had to go at a velocity. All right? So, again, we're going to start thinking about this in terms of these systems. And where does the momentum go? All right? Eventually we'll say, where does the energy go? Now, this is dealt with nicely down here on these slides. Okay, the first one says the velocity of A, the velocity of ball A after the collision, ball B, what is conserved during the collision, right? So if ball A in this case has 10 meters per second, this together is still going to be 10 meters per second, but it's going to be divided between the two balls, right? You can't tell exactly from here what the division will be, but it'll be some way between the two that they add up to 10. So that's why the two objects change their speed in the interaction. Not going to change the mass, but they did change the speed. Okay? And then again, yeah, the total momentum will be the sum of the momentum between the two. All right? And this is just a way of looking at the complete momentum of the system and what we mean by conservation. Okay? Now, you guys have heard conservation of energy before, probably. What does conservation mean in that sense? Well, what did you always hear about conservation of energy? Oh, come on. Middle school wasn't that long ago. They always say that, well, energy can never be what? Created or destroyed. Right? So this is what conservation means. There's a certain amount of momentum that goes into the system, and it's going to be divided amongst the other objects. Okay? Now, what happens if I do this? If I put this heavy brick on here, what do you think is going to happen to the second car? It's going to move faster or slower? Faster, right? Because what have I done to this? What have I done to this car's momentum?
You just like made it get
Added
heavier.
mass.
Right. Added the mass, so the total momentum is going to be the same, or as long as it's at the same speed, right? It's going to be the same. It's going to be greater momentum because there's greater mass. And sure enough, we do it. Right. Now you also notice what happened with the speed of this car. It didn't change as much, did it? It didn't slow down that much. Because, again, the momentum is going to be divided between the two, and it's going to keep a lot more of its momentum because it's the more massive of the two objects. All right? So, questions on that? Does that make sense to everybody? Now, the next thing that we want to look at is this idea of impulse. All right, so anybody ever hear that they have a problem controlling their impulses? Oh, come on. Somebody in here has to have heard that. What is that? What do I mean if I say that? Yes.
Like controlling your impulses.
Mm-hmm.
Like you're gonna want to do stuff, but you have to, for the greater good, you have to not do it.
Right. And usually we kind of lose control of our impulses and just, if you think, oh, I just wasn't thinking at that tiny little moment of time, right? And I forgot that I wasn't supposed to eat that. Or I forgot that I wasn't supposed to punch my brother in the hand. Right? Something like that. Just in that moment of time, because they made me mad, a snap decision and I did it. Okay? Now, that's very much related to this idea of impulse. Right? Impulse has to do with the force over a unit of time. Okay? And the impulse is increased if you increase the amount of time that is applied. So here, as you can see from this setup, we have force multiplied by time. All right. Now, the interesting part down here is that the impulse, in turn, is the change in momentum. Okay? And you're going to see this over and over again, right? We said force times the change in time is equal to mass times velocity. Now, there's a lot of underlying ideas that are coming out here because what does that tell us about force? Well, it's kind of a logical thing. If you have a certain amount of force, like if I take this car and I push this car with my hand with just a certain force, and I go like this is what happens. Now, if I apply the same force for a greater period of time, then what happens? Okay? What happens to the acceleration of it? Okay? So, there's greater momentum when you increase the amount of time. Right? And that makes sense. It makes sense for you to do that. If you're a baseball player, you know this inherently. Right?
Yeah.
Because they tell you, when you're batting, they tell you, as soon as you hit the ball, you can stop swinging.
No,
right? You follow through. Because you're going to increase the amount of time that you're hitting that ball with that bat. And the longer you hit that ball with that bat, the harder you're going to hit the ball. The more momentum you're going to get that ball. Or if you hit the ball with the smaller part of the bat, so that time decreases, you don't get as much momentum on the ball. Okay? So, the same thing in football with tackling, those sorts of things. Follow through. That's what they tell you. Shooting the basketball. Same deal. Follow through. Because the longer your hand is on that ball, pushing it, the more force or the more momentum the ball is going to have as you shoot it. Right? This is the idea of impulse, and those two are connected to each other. The amount of impulse that is given is going to be the same as the momentum of the object. All right? Now, this really isn't as interesting as all that until you get into things running into each other. Okay? So that's always more fun. Now, this brings us to the idea of collisions. And let me get this rolling here. I want to show this quick video because we need to talk about inelastic and elastic collisions.
Safety test crashes are a good way to see just how powerful a collision can be. When tons of metal collide at high speeds, the force and momentum is incredible. Well, what are the physics of this kind of event? We'll find out in this segment of Physics in Motion as we look at collisions. So what makes a collision? We all know one when we see one, but in physics, it's when momentum or kinetic energy is transferred from one object to another. Kinetic energy, you might remember, is the energy of motion, and momentum is the quantity of that motion. When objects hit each other, the collision falls into one of two categories, elastic or inelastic. When two objects collide and do not bounce away from each other, that's an inelastic collision. Momentum is conserved, but kinetic energy is not. Some of the kinetic energy is...
Okay, that's one thing that I would definitely make a note of. Elastic versus inelastic. And pay attention to the difference between those two types of collisions as this video progresses. All right, because this is really the big picture point of all of it.
Converted into heat, sound, and deformation of the objects. In a perfectly inelastic collision, the objects stick together, so their final velocities are the same. Think about the qualities of our paintball collision. Why is this inelastic? Do the two objects stick together when they collide? Are they moving with the same velocity after they collide? In both cases, the answer is yes. Now, let's do a problem using our inelastic paintball collision. In our collision, the system is the paintball and the barrier. So our problem asks, what is the final velocity of the two objects, the paint and the barrier, in this collision? The paintball has a mass of about 3 grams and velocity of 90 meters per second.
Okay, so an inelastic collision then, it's a collision where when the two collide, they become one. All right? So if you have if I were to have an egg and I just sliced it on the table right here by Anna, with Anna not being very happy with me, she would say, okay, that's an inelastic collision. Why? What happens? What happens to the egg? Smashes and becomes part of the deck. As opposed to this, it hits the ground, the tennis ball doesn't become part of the ground. Right? Or with this golf ball, it doesn't become part of the ground. Right? Now, you know that it's not perfectly elastic, meaning that there's going to be some energy that's lost. How do we know that? It's a brilliant question. For a brilliant answer. Yeah. But, yeah, the elastic on the inside is what's doing it, but how do we know it's not perfect? Well, yeah, it's good. It does stop bouncing eventually, right?
Yeah.
It gets smaller. Now, the other answer to that is if you hear it. Okay? When sound is given off, that's energy. So some of the energy is lost to sound. So it's going to be lost to heat. Before we heat up a little bit with friction. But if it weren't for those two, then the ball should now stack up at the same height each time. So it would be perfectly elastic. So an elastic collision is. Okay? Perfectly inelastic collision is at A going on because there's no change, there's no momentum as a single object anymore. Momentum would be this A disk object. It becomes part of it. Right? I used to have these other balls that were one of them as hard as you threw it down, it wouldn't bounce. So we kind of help students try to bounce it. But I don't know where I was years ago. But that was an inelastic collision. Yeah.
Big ball or this one?
It was like this big. I think the medicine balls pretty much is the same.
It bounced.
They do a little bit, yeah. But, okay? But they don't bounce very well because of the mass involved. And they're not real elastic. But, you know, and that's another thing is, and hopefully you're starting to understand this in physics, that just like in any other science, that there's hardly ever one or the other. Okay? You're not ever going to find a perfectly inelastic collision. Like an egg, it probably comes out a little bit. Right? Maybe some give it back to it. You have the shell of it. It'll still be separate, so they're going to be perfectly inelastic. Just like these are not perfectly elastic. There'll be some balls that are better than others, but regardless, it's not quite there.
So it has momentum. The total momentum of our system before the collision is the momentum of the paintball, because the barrier, which has a mass of 9 kilograms, is initially at rest and has no momentum. Remember, an object's momentum is equal to its mass times its velocity. We convert the mass of the paintball from grams to kilograms and get 0.003 kilograms. We then multiply this times the 90 meters per second velocity and end up with a momentum of 0.270 kilograms meters per second. When the paintball and the barrier collide, the momentum in the system must be the same both before and after the collision happens. The paintball and the barrier are moving together after the collision, so we add their masses to get the total mass of the system, which is the mass of the paintball, 0.003 kilograms, plus the mass of the barrier, 9 kilograms, for a total of 9.003 kilograms. Then we set the momentum of our system, 0.270 kilograms meters per second, equal to the combined mass of the paintball and the barrier, 9.003 kilograms, times the final velocity of the paintball and barrier together. In order to solve for the final velocity, we must divide the momentum by the total mass, and we end up with a final velocity of 0.03 meters per second. Keep in mind that this velocity only holds for the instant after the collision. Eventually, both the paintball and the barrier slow down until they're at rest at 0 meters per second.
Okay, so what was it in the beginning? Okay, so it went from 90 meters per second to 0.0, or 0.3 meters per second. That's a big change, right? But it's because you had something small going against something big. And if they become one, then that's not going to be that big of a difference, right? It's not going to be enough to make the whole move appreciably. Right? And the velocity there is very small, so it moves a little bit. Like if you had a camera and did one of those slow motion things, you might be able to see it kind of warping a little bit, but not much. Because again, it's a small mass hitting a large mass. It's something that you know, right? You understand this kind of inherently. Right? You have a collision between two people, one's really big and the other's really small. There's seldom any doubt who's going to come out better in that collision. Right? The small person decision or the big difference? Alright. So like if you're working on like with preschool or something and one of them ran into you, you're gonna be in better shape probably than the preschool. Right? It could be, right? But if you run into a big person, it's a different story, right? Now, let's move on with this.
Are both conserved, meaning the amount of momentum and kinetic energy in the system is the same after the collision as it was before the collision. Also in an elastic collision, no energy is lost due to sound, heat, or deformation, which is a change in the shape or size of an object due to force. In other words, dents, dings, and the like. Let's do a problem using an elastic collision with the help of Summer and Tom, and two rubber exercise balls. Okay, let's stop the video for a second while I give you some information about what's happening. Tom has a mass of 75 kilograms and is running at a velocity of -1 meter per second, holding an exercise ball. Summer has a mass of 50 kilograms and is running at a velocity of 4 meters per second, also holding an exercise ball. Okay, play the video. Now that's an elastic collision if I ever saw one. See how they bounce off of each other? If 50 kilogram Summer bounces backward with a velocity of -2 meters per second, what is Tom's final velocity? Remember that momentum is conserved in all collisions, so we always start with that, which is P sub I equals P sub F. Now, let's determine the initial momentum by adding up the momentum of each person. Plug in the equation for an object's momentum, which remember is its mass times its velocity. We do this for Summer and for Tom. Summer's mass is 50 kilograms, and her velocity is 4 meters per second. Tom's mass is 75 kilograms. His velocity is -1 meter per second. We make his velocity negative because he moves in the opposite direction of Summer. Multiply 50 kilograms times 4 meters per second and add it to 75 kilograms times -1 meters per second. Summer's initial momentum is 200 kilograms meters per second, and Tom's initial momentum is -75 kilograms meters per second. When we combine those two together, we get a total momentum of the system of 125 kilograms meters per second before the collision.
Okay, so that's going to be the steady no matter what. 125 in, 125 out. Now, the division of the two is the question mark, right? And that's going to be a function of the type of collision and the angles and all that.
Our initial and final momentum must be the same, 125 kilograms meters per second. So let's solve for the final momentum in the system for each of the two people. We plug in the values that we know. The total momentum is equal to 125 kilograms meters per second, which is equal to the sum of the momentum of Tom and Summer. Summer's mass is 50 kilograms and her velocity is -2 meters per second, which we multiply together to get her momentum. The velocity is negative because it is in the opposite direction of her initial velocity, which we made positive. We also plug in Tom's mass of 75 kilograms times his final velocity, which is what we are solving for. We multiply 50 kilograms times the -2 meters per second to get Summer's momentum after the collision. We get -100 kilograms meters per second. We're solving for Tom's final velocity, so we add 100 kilograms meters per second to both sides of the equation. That's the first step in getting Tom's final velocity by itself. We end up with 225 kilograms meters per second on the left-hand side of the equation and the expression for Tom's momentum on the right. The final step is to divide both sides by Tom's mass of 75 kilograms, which gives us Tom's final velocity of 3 meters per second. The final velocity shows us that they also bounce backward and move in the direction opposite to their original motion, because the sign of the final velocity is opposite the sign of the initial velocity. Got it? Because this collision was elastic, kinetic energy was conserved. In this segment, we've learned how the term collision is
Okay, so now what I also want to cover, and let's see if I can just go back. There we go. And this is kind of a good illustration of it, is the difference with these elastic and inelastic collisions. Again, the two become one. All right. Now, the next thing that I want to at least introduce you to is this idea of energy. Okay. And the momentum and energy and the work and all these things, it's going to take us several weeks to get through. And so I want to kind of lay the groundwork right now. So you're likely to feel a bit confused after today's class. That's okay. We'll continue to work through it. But I can think of no better way to start this off then with this, which is one of my favorite physics videos to share with the class. So this guy is was a professor at MIT. I think he retired. But watch this closely.
Return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 to 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks the building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer.
Okay, so was that an inelastic or an elastic collision? What tells you that it was an inelastic collision? Yeah.
The glass broke.
The glass broke and you heard it, right?
Yep.
So that you get the deformation of the object that it hit. You have the sound, right? And so obviously the momentum of the ball, heavy ball, is kind of what he was saying. It's about 15 kilograms is a little over 35 pounds. You get enough speed on that thing, it certainly will do the job.
Of the conservation of mechanical energy, that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0.
Almost got it. Dang it. Okay, so this is where he starts.
1, 0.
Watch carefully. Oh. Oh, I had it too. I'll get it this time. Okay, and that's where it came back up. Now, notice one thing, right? It's not the same place. Now let's talk about that phenomena here. All right. Sorry. I need my Okay, so he has kind of the same thing here. And just to recap what he did, he did it up, right? And then get it close to his face. Watch this.
Come on, Dory.
Okay, so then when I go here, right? Okay, now why doesn't it come back up to where it started? Why? Yes.
Changing direction.
Okay, got to change in direction. What is it going? Okay, you get gravitational. Air resistance, yeah. Okay, because if I put this much energy into it, I should get it right back, right? If you have conservation of energy and conservation of choice. However, some of it's going to go away because of air resistance and what else? Good. Friction, okay? Because if you look up here, regardless of how that thing's hanging, whatever it's hanging from, there's going to be some friction with the line to the whatever projection it is. Okay? You can't, nothing's ever perfect on planet Earth. All right. There it goes. You can't make a perpetual motion machine. You ever see like the grandfather clock that has the pendulum down at the bottom? It's fixing back and forth. You gotta wind it up or give some electrical energy to it. Because even with perfect gears, and those gears are made darn near perfect, there's going to be some friction. There's going to be some loss of heat energy from loss of sound. That's why you hear tick, tick, tick. Right? So some of the energy goes away. Right? But it's interesting to think about what he's doing. Why am I giving this energy by taking it up? What am I fighting against? Gravity. Right? So when you have a force pulling on something, if you're going to go other way with it, if you're going to go against that force, you have to supply energy. So this is what we call work. Okay? We say energy is work and work is energy. You find energy as the ability to do work. All right? So in order to put this thing in to motion, I have to do work on the system. I have to put energy into it. Otherwise, it's just going to sit there. Just hang out. an outlet suspended by the wire. Okay? The only way that it can ever get in motion is for somebody or something to put some work into it to make it happen, right? Got a little collision there, right? What happens to the speed of the object? Slows down, right? Okay. So that is the beginning, and what I want you to think about, start thinking about is, well, what kind of energy are we supplying here, right? We have two different types of energy. Okay? And this is going back to your middle school days. You look at the next slide down there. We go here.
Physics works, and I'm still alive. See you
Yay.
Wednesday.
Okay. Now, we have two different types of energy that was on display there. We have this type of energy. We have kinetic energy. You guys have heard of kinetic energy, I hope. Yes? Make your middle school science teachers happy. What does kinetic mean? Moving, right? Anything that involves motion, right? Probably some of you when you were younger were described as being hyperkinetic. And you couldn't sit still, right? Constantly moving, constantly doing something. I know I was for sure. But that's what that means. And if you hear kinetic, it's involving motion. You can study something called kinesiology in college. What? Right. Okay? That's studying things in motion. Typically, yeah, as Ella said, it's something athletic. Yes. Yes. Okay? So you may be like taking swimmers and videoing them and helping them figure out how to make their strokes perfect, their soccer players, and how to kick the ball a little bit better, change names or foot and all those things. But it's motion. Dealing with motion. So that's what kinetic energy is. Kinetic energy is the energy of motion. It depends on mass and velocity. Okay? And kinetic energy, I'm going to write this here for our friends at home. Kinetic energy equals 1/2 the mass of the object times its velocity squared. All right, so, and m equals mass, and v equals velocity. Okay, so if the object is not moving, if it has a zero velocity, what is its kinetic energy? 0, right? Doesn't matter what the mass is. If it's not moving, the velocity is 0, it has no kinetic energy, right? And this isn't quite moving, but it isn't quite stopped yet. But right here, our outlet has 0 kinetic energy because it's not moving. All right? So, as we would say, it has no energy. It's just hanging out there, and our energy, kinetic energy is entirely based on the mass and the velocity. Now, different objects are going to have different kinetic energy. Which of those is going to have the most kinetic energy of those three? I'm going to put both of them together. What do you think? The truck or one of the two motorcycles? Most kinetic energy. Huh? Logically, it would be this guy, right? Because it has a big mass and it is traveling at equal speed to one of the motorcycles and more than the other. So it's going to have high values for both mass and velocity. And then this one right here is going to have to be the least. because the smaller mass and the smaller velocity. Now, the kinetic energy is typically, if we think of that as being what is going to be the most effective in causing damage during a collision, right? The higher the kinetic energy, the bigger the damage that results. Which of those two values, mass or velocity, affects kinetic energy more? I'll put the formula back up. The velocity, right? Because that term is squared. So, and this goes back to my constant refrain on giving people heads up as they become new drivers. So, it matters less the size of car that you're driving when you're in a collision, and matters more the speed that you're traveling. Right? Because since velocity is squared for kinetic energy, if you double your speed, you're going to quadruple your energy. If you triple your speed, go from 20 to 60, then the collision will be 9 times as bad. Right? Because it's all about transferring that kinetic energy and the effect that it's going to have on whatever you hit and you as well in your car. Mass does make a difference. That's why they will have separate speed limits a lot of times for semi-trucks, the large masses, because you don't want those things going 100 miles an hour. And certainly not be in front of one of them. Okay? Because there's not going to be much chance for you if that happens. So, that is kinetic energy. Now, the last part of energy this is the last thing I want to mention is this idea of potential energy. Okay? I don't know why that happened, but come on. There we go. Okay, so for potential energy, if someone talks about potential, what is potential? Like, have you ever had someone say to you, oh, but you have so much potential? What does that mean? Yes. Like the ability to do it, right? You're not doing it, but you have the ability to do it, right? So usually that's like parents trying or some other adult trying to tell you that you're being lazy, right? There's potential to be better if you're not doing it. Well, it's the same thing with energy, right? When you talk about potential energy, it means it's stored. It's waiting to do something. It's like money in the bank. Money in the bank is not doing anything for you, but it's not being spent. It's not going away. It's still there, right? So when you get money, you have those choices. You can either potential, save it, or kinetic, do something with it, right? So when I pick this up, when you move the object upwards against gravity, you're doing work and you're storing that work energy as potential energy. This is what's happening here. Okay? This has more potential energy than at the bottom because we pulled it against gravity. Right? So the potential energy is sitting there, and then we can convert this potential energy to kinetic. And that's why it moves. Notice at the top over there, what happens? It stops. Okay? So it goes from maximum potential energy to maximum kinetic to maximum potential. Kinetic potential, like that, back and forth, and the energy switches back and forth. Okay? Now, side note, that I can do the pendulum, but I don't want to see all you doing pendulums with these outlets, all right? be good. But that is the overall point, and make sure that you understand the difference between it. Your homework is a couple of problems with momentum, and then some reading and that to get you ready to do more serious discussions on kinetic and potential energy. All right, so make sure that you're doing that. I know that's a lot of information for one day, but we're going to have lots of days to really hash this out. All right, so you can get to work on your homework, hang out, I'll get Anna her test, if you can finish up. And we'll say goodbye to all our friends at home. See ya.